Any data scientist will tell you that the key to being able to do your job is having access to data. But imagine having all the data you need, but it's in just one giant text file. Well, that's probably no good, right? The data has to be useful. It needs to be in the correct type of database. And in order to do that, you need to form a strategy. First, you need to identify the type of data that you're dealing with. Is it structured, semi-structured, or unstructured? Understanding the type of data that you have will go a long way to deciding what sorts of technologies you can implement to store and serve that data. But storage isn't the only key. You need to understand how you're going to use that data. This part is massively important. One of the first questions I ask when dealing with customers or managers about their data is, how do you plan on using this data? If you plan to query the data constantly, that's a very different usage pattern than if you plan to query it monthly or even quarterly. If you plan on mining your data for insights, that's very different than just displaying the most recent value on a dashboard. If you can understand your query patterns up front, you'll have a much higher chance of selecting the right data service for your system. But what does it mean to understand your query patterns? Well, in fairness, that's not a great term to use. So, put in a simpler way, what you're really trying to understand is your storage and performance requirements. Okay, but what does that mean? Well, imagine you have this dump of data. You know that you're going to use that data, right? Well, the question is, how? So, for example, is your plan that you'll perform simple lookups on that data? Just periodic simple requests for whatever's in there? If so, then you don't really need anything complicated, right? Then again, if you're planning to do some more intense database queries that join different parts of the dataset or return content conditionally, then you're going to need a database that can support those types of queries. But what if you plan to augment the data? For example, what if you plan to allow users to create, update, or even delete content in the database? At that point, you're not talking about a simple store, but a store that can be manipulated. It probably also means that you want to institute some security measures on that data too. But what about deep diving the data? What if you want to comb through all the data looking for correlations between things? What if you're looking for much more complex data analysis than just simple joins and conditions? At that point, maybe you're talking about machine learning. Well, you're probably not going to do that with a text file, right? And the final thing to consider when you're thinking about how you're going to use the data is actually the speed requirements of your data operations. That's actually quite important. Lots of managers will say they need all their data as quickly as possible, and that's generally just not true. If you really think about your data, you're probably going to find that you need some of it quickly, and most of it can be archived for background activities. Now, it's also worth considering what your transactions and operations look like. In fact, ideally you can group a number of operations into a single transaction. But what's a transaction? Well, a transaction is one or more operations that are grouped together. An operation is something like a create, update, or delete. So imagine a scenario where you want to create an entry in your database about something like a person. Well, the information about that person may be in multiple different tables in your database. Now let's imagine that one of the operations fails during the process of creating the various entries. Well, now what you have is incomplete data in your database. Worse, your database may now be corrupted. One thing you can do is wrap all these operations in a transaction. But what does that do for you? Well, it groups all the operations into what appears to be a single execution. It means that if anything inside that transaction fails, then all the operations are rolled back and your database remains incorrupt. If everything works properly, then and only then will all the operations be committed. Transactions are generally based on the idea of ACID, that is, atomic, consistent, isolated, and durable. The idea is that a transaction performs a single task, even if it's multiple operations, atomic, and it ensures that the database is only updated when all the operations within the transaction complete successfully, consistent, that it doesn't interact or interfere with other transactions, isolated, and is capable of handling errors, durable. Now, there are generally two kinds of transactional databases, OLTP and OLAP. OLTP databases are generally faster, support more users, and handle large volumes of data, but they only support very simple transactions. OLAP databases support fewer users and aren't as fast, but they can support very large and complex transactions. Now, when you're strategizing about what sort of database you're going to use and how you're going to use it, it's also worth understanding just what kind of data you have. The types of data you have can impact the database selection. While this might be simplistic, typically data boils down into one of three categories. Specifically, your data can be what's referred to as product catalog data. Basically, this is the type of data that can be well defined but also unique by type, like a product. Think of things like shoes, cars, clothes, and any sort of widget. Each product has very specific properties, but the properties of one product are definitely different than the properties of another product. Your data can also be media, so things like photos and videos. In those cases, there are some properties that each of these files share, but at the end of the day, every video and every photo is different from every other video and photo. And the third category for your data is what we refer to as business data. Business data can be lots of different things. It can be complex or simple, large or small. Even the way you deal with business data can be different. Some is critical and you need it instantly, and some is regulatory and just needs to be archived for record keeping. But business data is generally well defined, and you know what the data is and how it all relates to each other. Knowing the different categories of data you have can greatly impact what sort of data service you implement. For example, product catalog data is generally semi-structured. There's lots of different types of products out there, and you know what properties they have, but each product type is different from another type of product. So this type of data is what we call semi-structured. And one of the best services in Azure for semi-structured data is Azure Cosmos DB. Meanwhile, if you have photos and videos, you're talking about data that's totally unique from one file to the next. And that's what we call unstructured data. In Azure, Blob storage is a really good service for unstructured data. And then, if you have business data where everything is well defined and properties and relationships are configured and set, then you're really talking about structured data. And the best data service for handling structured data in Azure is Azure SQL. Probably the most basic and yet fully featured data service in Azure is Azure Storage Accounts. There's a whole bunch of different services baked into Azure Storage Accounts though. Specifically, Azure Blob Storage is all about being able to store, well, blobs. Blobs are typically considered unstructured data, and this can be super handy to store just about anything you want. It can be files, logs, videos, JSON, or really anything. Now, similar to blobs is Azure File Shares. File shares are also about unstructured data, but specifically geared towards file management. You can create folders and files and then assign whatever permissions you want, just like any on-prem file share. Then there are queues. Queues are useful for semi-structured messages. In other words, you can deliver small messages to a queue, and any other app that's interested in those messages can listen to the queue and take whatever action it wants. A good example of queues in action is chat apps. Now, the reason they're semi-structured is because you know exactly what properties a message can have, but the contents of a message can be just about anything. Next, there's Azure Tables. Tables are very good for semi-structured data. They have a certain set of known properties, and then you can add whatever other properties you want. As a result, they can be rendered almost like a table. But at the end of the day, the properties between one entry versus another in the very same table could be completely different, and we'll touch more on that later in the course. And lastly, there's the concept of disks. This can actually come back to file shares a bit. Because of the nature of file shares, you can actually use Azure Storage Accounts as a disk for multiple virtual machines in the cloud. And this can make things way easier for you to share data between systems. But why use storage services in Azure? What are some of the advantages? Well, really, there's a ton of advantages, but just to name a few, storage accounts in Azure are accessible from virtually anywhere in the world. They're highly available too. Why? Well, because storage accounts are fully managed by Microsoft in Azure. Everything's backed up, redundant, and kept up to date, and there's virtually zero downtime. And because it's in the cloud, it means that storage accounts are highly scalable too. Need more storage? No problem. Need more bandwidth? No problem there either. And while it should go without saying, we'll say it anyways. Storage accounts are very, very secure. And as a last point, let's quickly talk about one type of security, and that's encryption. There are two ways that your data is encrypted. The first is at rest, and what this means is that when your data is in the database, it's encrypted. So let's pretend that somehow someone was actually able to get a copy of your database, or even the hard drive that it's stored on. As outlandish as that might seem, there are still protective measures in place. Your data is encrypted and requires very specific keys to gain access. So if someone had the actual database, they wouldn't have the keys, and so your data is secure. Now, the other way data is encrypted is what's called in transit. So imagine a client-side application connecting to your database and downloading data. Well, that connection is secured. That means that if some nefarious party was sniffing the packets as they went from server to client, the data would be encrypted and the sniffer wouldn't be able to sniff anything at all. Earlier in this course, we talked about different types of data structures. Specifically, we mentioned the three main types: structured data, unstructured data, and semi-structured data. Now, each type of data structure serves a very specific purpose and has its own pros and cons. So let's take a bit of time here and discuss each of those structures. First, let's talk about structured data. Now, structured data generally relates to data that has a sort of relational model. In other words, the data has a very well-known set of properties and relationships. For example, imagine a family tree. Each person in the family tree has a known set of properties: a first name, a last name, eye color, height, and so on. Meanwhile, each person has relationships with other people: siblings, parents, children, and so on. The data is highly structured. As a result of that data being so well defined, structured data is generally housed in tables. A table can be fully defined and known to contain a very specific type of data. Each thing in the table, like a person, has a known set of properties, like name, eye color, and so on. And because each property is well known, you can set parameters for each of the columns of information in that table. And these constraints can limit the possible values or even limit the width of the data in that column. And of course, since we know the properties so well, we can even forcefully set the data types, like height must be a number, name is a string, and birth date must be a date. Now, structured data is defined at design time. The database is created and the data is understood already at that point. You can't create the database on the fly or even put any dynamic data in it at runtime. You need to understand your data before you build the database. And each different piece of data, like a person, a truck, a vegetable, or a dog, needs to be created as its own table. So in that example, I'd expect to see a people table, a trucks table, and so on. Now, because the intent is to place data into those tables, and those tables have all the properties that define what the data is, the tables and even the whole database have to be designed before the data is populated. For example, let's say you had an empty database and now you want to store a person in it. Well, you can't do that. There's no people table. So now let's say you create the people table. Well, you still can't put data in the table because it doesn't have any of the needed properties or columns. So you really need to design the whole thing before you use it. But that doesn't mean you have to fully design the entire database and all the tables and properties before you can use the database. You can make changes. Your database can evolve. The challenge is always that it's slow to make those changes. There might be lots of systems using that database, so making a change to the database necessarily means changing its structure. So any consumers of your database will be impacted by the change. So changes need to be handled with care. For example, imagine you wanted to simply add a new property to your people table, like hair color. So you go ahead and add a new column to the table. But what happens to all the data that's already in that table? Well, making that modification is effectively like performing a bulk update on all the data in that table for your new column. Does that invalidate the data you already have? Should they all have default hair color? Or maybe we'll consider all of them bald, so you can see the challenge. But once you do have your data structured and nicely defined in a structured database, you can take advantage of the database's query language. Structured data allows you to use very powerful query languages that can sift through your data very quickly to find whatever you're looking for. It can quickly calculate things too, and that way you can get some pretty exciting metrics and insights. Now, after structured data, we have unstructured data. Unstructured data is basically the exact opposite of structured data. The most common example of unstructured data is things like binary files, audio files, or image and video files. Those types of things are called unstructured because every individual item is unique from all the other items. You cannot say that every image in a folder has a certain set of content properties that they all share. Now, under the hood, unstructured data is stored in a non-relational database, commonly referred to as NoSQL. All that means is that there's a piece of data, it has an ID, but its content is just about anything and there's no defined relationships between different bits of data. Now, the thing with unstructured data is that it can't be defined at design time. You simply can't know what the data is going to be before you get started. And that means that the data you collect, store, and read is always in its raw format. The actual structure of the data is only defined when the data is read. Okay, but what does that mean? Well, imagine something like a PDF file. You have absolutely no idea what's in that file or what it's going to look like until you read it. The title and the file size can give you hints, but what's actually in that file is totally opaque until you read the file. Now, NoSQL databases are very common these days. In a lot of ways, they're preferable to relational databases, but that's a discussion for another time. If you do find yourself looking at NoSQL databases, there are a few different types to consider. For example, a key value store allows you to simply store key value pairs. The key is a common property for all the entries in the database, and there's always a value. But the content of that value can be absolutely anything. And one of the first and most common NoSQL database types is a document database. These store objects, which are referred to as documents, and are tagged with all kinds of metadata that can help with searching for those documents. Next, there's a graph database. A graph database is all about defining relationships between different items in the database. The point of a graph database is to be able to query for data specifically based on their relationships to each other. For example, imagine a person. A person can be defined once in a graph, and then that person can have a family, that person can belong to a sports team, and that person can work in an office. Now, depending on what information you're trying to attain, you could run different relationship queries in a graph database and you would find that person, or not. Microsoft themselves have implemented a graph database to back role-based authentication in Azure. And lastly, there are column databases. These are about storing data as columns rather than as rows. And the columns can be defined at runtime, and that can allow for some flexibility in performance. Now, these types of databases are not as common as others. And finally, we have semi-structured data. Semi-structured data is, as you would expect, a hybrid of structured and unstructured data. Semi-structured data has the advantage of being able to provide some means of structure to data, but obviously it's going to be way less organized than actual structured data. Now, the organization is generally done through tags. By tagging data in a certain way, you know what it is, or even what's in it, without having to fully read the data. But since it's not really structured, it has to be stored in an unstructured database. So semi-structured data is still stored in NoSQL databases. Azure storage accounts offer lots of different built-in security features, and there's tons of advantages and benefits to that security. For example, Azure storage accounts offer encryption at rest, and that means that the data in the database is completely encrypted while inside your database. So if someone ever actually got their hands on your database, they wouldn't actually be able to read your data because the database is encrypted. Storage accounts also perform encryption in transit. What that means is that anytime you read or write data, the transmission of that data is encrypted too. So if someone were to sniff your communication, they wouldn't be able to read the data. And like most Azure services, Azure storage accounts also include user access control. And that means that you can very easily pick and choose who actually has access to your data. And this can be users, groups, or even applications. Now, storage accounts even support CORs. And what that means is that access to storage accounts from across domains can be restricted to only certain domains. And finally, storage accounts can include access auditing. So any activity performed against a database itself can be tracked and then reviewed if needed. Now, for storage accounts, and in particular blobs and queues, authorization security can be managed in a couple of different ways. The first way is by using Azure Active Directory Authorization. Azure AD can be used to create managed identities, or you can create your own app registration. In both cases, you're effectively saying that there's some identity defined in Azure AD that can then be used to grant access to your storage account. So in that sense, an application can be treated exactly like a user. Now, once you have these identities, whether they're users or apps, you can use the access control features for data services like blobs and queues to grant certain kinds of access to your data. You don't have to give full administrative rights, you can give read-only if you want to. Now, another way you can authorize access to storage accounts is through storage account keys. If someone has a key, then they don't need to have an Azure AD identity. This is another way to grant access. Storage accounts always include two keys, a primary key and a secondary key. There's technically no difference between them. Well, the key values are different, but what I mean is that one isn't more special than the other. If you have a storage account key, then you have full access to all the data features in the storage account. So if you have the key, then you can access the blobs, the files, the queues, and the tables in that account. Keys are extremely easy to implement. There's a single string, and generally most Azure libraries and services know exactly what to do when you give them that string. So there's not a whole lot of work involved in using these keys. Now, all services in Azure are usually fronted by an API, so storage accounts are no different. The way these keys work is that they serve as an authorization header value when performing the request. If the key is valid, information will be returned. If not, you'll get an unauthorized response. Now, if there's one problem with these storage account keys, it's that they're very powerful. So you want to make sure that you're protecting your keys. Now, the first step is to make sure that you're only using them with trusted applications. Don't just paste your key on a public wiki, right? Share your keys with only the applications that actually need them. And even then, you should have a plan to regenerate the keys on a regular basis. And what that means is that you can actually ask Azure to refresh your keys. And what that means is that a new set of keys will be generated. So anyone using an old key will immediately be unable to authenticate. And that's why there are two keys. You can have all your apps using, say, the primary key, and then you can refresh the secondary key. If none of your apps are using the secondary key, then nothing will be affected. Then you can move all your apps to the secondary key. And then once every app is migrated to the secondary key, you can refresh the primary key, and there's no downtime. But there's actually another type of key in storage accounts too, and that's shared access signatures, or SAS. SAS keys are used for instances where we want to grant access to our storage account to untrusted or third-party clients. In this case, SAS keys are linked to very specific data services and even specific containers in those data services. So if you wanted to grant access to a specific file share but nothing else, you could do that with a SAS key. Now ultimately what this means is that you can use SAS keys to control access to individual storage objects. Now this can be very powerful if you truly want to give external entities access to your database directly. And SAS keys work similarly to storage account keys. They're like a security token, so users attach the keys to the URI request. Now, as powerful as SAS keys are, there's actually two different types. That gives you even more control. The first is a service-level SAS, and that's the SAS key that allows you to grant specific access to specific data services deployed in your storage account. But there's also an account-level SAS key, and that allows you to grant access to the entire storage account in much the same way that we do with storage account keys. There's actually one more layer of security that you can implement too. You can control access to storage accounts through network access. By default, storage accounts accept requests from clients on any network, but you can actually set up your storage account to limit access to only specific virtual networks in Azure. From there, you can manage various default rules even further. You can even go so far as to limit access to your storage account to only very specific IPs. Now, the whole point of these various layers of security is to make sure that only the necessary users, groups, services, and applications actually have access to your data. And finally, it's worth mentioning the Azure Storage Accounts Advanced Threat Protection, or ATP. ATP is a built-in layer of protection in Azure that detects unexpected or unusual behavior patterns. This can help prevent potential harm to your data. In fact, Azure can automatically generate security alerts and let you know if something odd comes up. One of the most common examples is when a database gets a sudden influx of data. Azure will automatically detect that the traffic flow is different than it has been in the last 7 or 30 days, and it'll then flag the activity for your review, so you can decide whether or not to do anything about it. Now, this is all done using Azure Defender for storage. You don't have to implement it. Azure does do some basic analysis on its own, but if you want to have full protection and continuous threat analysis, Defender is the tool to use. This will even work for scenarios where hierarchical namespaces are being used, like with data lake storage. In this demo, we're going to walk through creating a simple console application that can upload and download blobs in an Azure storage account. Now, before we get started, this demo assumes that you already have an Azure storage account set up in Azure and that you have full access to it. Alright, so the first thing we're going to do is we're going to open up Visual Studio Code in our desktop. Perfect. Now let's create a simple console application. Open up the terminal by clicking on the Terminal menu and choosing the New Terminal option. Great. Now in the terminal at the bottom of the screen, let's create the new console app. We can do that by typing .NET space new space console. Excellent. Now we have a console application. Now, before we can start writing code, we need to get our project ready. Our intention here is to upload and download files to our Blob storage in Azure. So let's create a folder to put these files into. In the terminal, let's type the command mkdir space data. Now notice how the folder now appears in our Project Explorer on the left side of the screen. Now the next thing we need is the .NET storage account libraries, or NuGet packages, and that allows us to communicate with our storage account. So once again, in the terminal, let's type the following command: .NET space add space package space azure.storage.blobs, with a capital at the beginning of each of those words. Now let's execute that. Perfect. We now have a reference to a library that'll allow us to talk to our Blob storage. All right, now we can start coding. So let's click on the program.cs file in the Project Explorer on the left-hand side of the screen. Okay, now when we connect to and interface with an Azure storage account, you need a connection string. And we'll touch on that a little bit more later, but for now, let's replace line 9 with the following line of code. var space connection string space equals quote replace space me quote semicolon. Good. Now, generally a connection string should be retrieved from an application settings so that it can be configured at runtime. It would also allow for encryption in an Azure Key Vault if you wanted to go that far. But for our purposes, we're going to hard code our connection string. Okay, so the next thing we want to do is connect to a Blob container in our storage account. So let's add a blank line after our variable and then write a few lines of code to establish that connection. var space container equals new Blob container client with a capital B and 2 C's, open bracket, connection string, comma, quote, demo, end quote, end bracket, semicolon, and then on the next line, await space container dot create if not exists async, open close brackets, semicolon. Now first, I want to call attention to our container variable creation. Notice that I've hard-coded a value called demo in there, and that's going to create a container called demo. This is another area that could be made configurable. Also notice that it's all lowercase and has no special characters. That abides by the Azure naming rules. Anyway, notice that Azure Visual Studio Code is complaining about our Blob container client object, and that's because there's no reference to the class in our directives at the top of this file. So let's fix that. Let's add the following directive to our list: using space azure.storage.blobs, semicolon. Good. Now notice that Visual Studio Code is still complaining about our container creation command. And that's because it's an asynchronous command that we've put in a synchronous method. So let's replace the void in our method to async task. Async space task with a capital T. Of course, now it's complaining about the task object. And that's because we need another using directive. So below the system directive, let's add the following directive: using space system.threading.tasks, semicolon. Huzzah! Our code is now clean. All right, so now that we're connected to our container, now we want to upload a blob to that container. So to make things easy on us, let's create a file that we want to upload. In the Project Explorer, right-click on the data folder that we created earlier and select the New File option. Now let's call that new file demo.txt. Good. Now Visual Studio Code shows us the new empty file. So let's just put some dummy text in there so that it has some content that we recognize. I'm going to type hello space world. And let's save the file with a Control S. Perfect. Now let's go back to our code by clicking on the Program CS tab. And now let's drop a couple of lines down from our container create command and create a reference to our file. We can do that by typing the following: var space file name equals quote demo.txt, semicolon. Now this command is hard-coded to the name of the file, so you can see that you have lots of options for making that much more dynamic if you want. Now let's upload that file. Let's type the following code right below our file reference: var blob equals container.getBlobClient, open bracket, file name, close bracket, semicolon. And then below that, await space blob.uploadAsync, open bracket, path.combine, open bracket, data in quotes, comma, file name, close bracket, comma, true, close bracket, semicolon. Okay, so what we're doing in this code is we're creating a connection to a blob in our container. Then we're uploading our file into that blob from the data folder that we created. The true value is telling the command to override any blob that might already be there with that name. Anyway, at this point, we've now written code to upload a blob. So let's write the code to download a blob. First, let's create another folder. So in the terminal, type the following command: mkdir space downloads. Good. So now we have a new empty folder in our project list. Now let's go back to the code. First, let's fix our typo and make that a capital P in path. Now, notice that Visual Studio Code is actually complaining about that path command. And that's because there's no reference to that class in our directives at the top of the file. So let's fix that. Let's add the following directive to our list: using system.io, semicolon. Good. Now that fixes that. Now on line 19, we're uploading a file to our blob storage. Now let's download that file to our downloads folder. So let's drop a couple lines down and write the following code: await space blob.download to async, open bracket, path.combine, open bracket, quote, downloads, end quote, comma, file name, end bracket, semicolon. Now this code uses our existing blob reference and then selects to download it to our downloads folder. Now it's worth noting here that I'm using the same file name variable, but I didn't have to. I could upload my file to blob storage with any name and then download it with any other name. And that can be valuable if you're appending unique strings to your file names in storage, but want it to look normal when downloaded. Anyway, I'm keeping this simple by using all the same names. So now let's see this in action. But oh wait, we need that connection string for our storage account. So let's do that. Let's flip over to the Azure web portal in our browser. Next, we need to navigate to our storage account. Now I called mine sbdemo10, so I'm going to search for that and select it from the search results. Good. Now in the left-hand menu, let's select the Access Keys option in the Security and Networking section. Excellent. Now in this screen, we're seeing a few different keys and connection strings. Let's copy the connection string under the Key 1 section. To do that, click on the Show Keys button and then copy the value from the connection string field. Now let's flip back to our code. Good. Now on line 12, let's replace our dummy string value with the connection string value. Perfect. Now we're finally ready to rock. Let's save the file with Control S. Now in the terminal at the bottom of the screen, let's finally run our console app. To do that, type the command .net space run. Well, that seemed anticlimactic, didn't it? But let's see if it worked. First, let's flip back to our storage account in our browser. Now let's click on the Storage Explorer option in the left-hand menu. And now let's expand the Blob Containers section. Hey, look at that! We have a container named Demo. Nice! Now let's click on the container. Wow, look at that! We have a file in there called demo.txt. That's perfect! Now let's see if the download worked. Let's flip back to Visual Studio Code. And in the Project Explorer, let's expand the Downloads folder. Hey, look at that! We have a demo.txt file in there too. Let's click on it. And look at that, it says Hello World, just like our input file. Now let's make sure this is working as we expect. Let's click on the input demo.txt file, and let's change the text to something else. I'll just add some random text to the end in here. Good. Now let's go back to the terminal and run the application again. And now let's go check our output file. And look at that! The text is updated. Fantastic stuff! So you've successfully created a very simple console application that can connect to a storage account, create a container, upload a blob, and download a blob. Great job! Azure storage accounts or storage services are incredibly useful. They're simple, easy, and intuitive. But despite being simple and intuitive, they aren't short on features. For example, storage accounts are a managed service, and that means that Microsoft handles all the upkeep and maintenance for you. They're also extremely scalable, and that means that they can handle massive amounts of load both in terms of storage and continuous use. And of course, storage accounts are secure. Your data is protected in transit and at rest. Plus, you can restrict access in tons of different ways to make sure that only the consumers that you want to have access to your data can actually have access to that data. And one more feature of storage accounts is that they're durable. Your data is kept on a redundant system and failover is automatic. If your data center that's housing your data was hit by a meteor, it's unlikely that you or your consumers would ever know. Now, storage accounts in Azure support 4 different data types. You don't have to pick just one either. You can actually use a single storage account for any combination of these data types. And what are the data types? Well, the first type is blobs. Blobs are pretty much anything you want them to be. They can be documents, log files, binaries, JSON, or really just about anything. Then there are files. And files are like blobs, except that they're specifically designed to be implemented in a file sharing system. In fact, you can use a file share across virtual machines, or even to replace an existing on-premise file share. Next, there's the concept of queues. Queues allow for messages to be sent between different applications asynchronously. A message is placed on a queue, and another consumer picks up that message. It's a mechanism for services to communicate with each other, but indirectly. And lastly, there's table storage. Tables allow you to store any type of data you want. The caveat is that the data is stored as one or more properties, and that entry must have a partition key and a row key to identify the data. Now, there are some limits built into Azure storage accounts that you should be aware of. First, there's a limit to the total number of storage accounts that you can actually provision in your tenant. You can deploy a maximum of 200 storage accounts. There's also a limit to the amount of data that you can store in a single storage account. The maximum amount of data you can store is 500 terabytes. Now, those limits are a technicality. Microsoft is very motivated to have you use their systems. So if you were to find yourself in a situation where you needed more storage accounts, or you needed to store more data in one of your storage accounts, you could contact Microsoft and they'd likely work with you to work around those limits. I can say that because I've had to do that myself. Now, Azure storage accounts also come in 3 different versions. The first and current version is General Purpose v2 or GPv2. GPv2 includes all of the data services like blobs, files, queues, and tables, and it supports all of the latest features for each of those services. It's also been optimized to deliver the lowest cost per gigabyte usage. General Purpose v1 or GPv1 is the previous version of storage accounts and includes all the data services, but it does not include the latest features. For example, cool and archive storage isn't included. Pricing is still pretty low for GPv1, but because the service isn't optimized, sometimes there's more behind-the-scenes operations, which can result in higher cost depending on what you're doing. And finally, there's the blob storage account type. You can probably tell from the name, but this account type is limited to just blob storage, and even then, it doesn't have all the same features. However, the pricing is pretty similar to GPv2. Now, in Azure, all your data is ultimately stored on disks, and in Azure, there are only 2 types of disk storage. First is managed disks. Managed disks are, well, managed. They're completely and totally handled by Microsoft and are totally opaque to you. Whether they're on a RAID system, a giant partition drive, or due for updates, you don't care. Microsoft will completely handle that behind the scenes for you. But another type of disk storage is unmanaged. Now, with unmanaged disks, basically you're bringing your own disks to the party. Now, in cloud terms, those aren't real physical disks. Generally, that means that the virtual hard disks that you're using in systems like virtual machines are actually coming from an Azure storage account. Typically, you use page blobs to do that. And lastly, while there are different kinds of disk storage, there's also different kinds of disks altogether. Now, the first kind of disk is a standard disk. Now, this is your everyday hard drive. Nothing special here. But then there's premium disks. Premium disks are always solid-state drives. That means that they're much, much faster. But it also means that they're more expensive. So if you're in a situation where every tiny bit of performance is important, then look to use premium drives. In this demo, we're going to create an Azure storage account and an Azure virtual machine. In later demos, we'll use a console application on the virtual machine to upload and download large amounts of data to and from our storage account. Okay, so the first thing we need to do is head over to the Azure web portal in our browser. Excellent. Now in this demo, we want to move large amounts of data to and from a storage account. So the first thing we need to do is create a storage account. So at the top of the screen, let's select the Create a Resource option. Good. Now let's search for storage accounts in the search field. Great. Now let's click on the Create option in the resulting Microsoft Storage Account object. Good. Now the first thing we're being asked is to select a subscription and a resource group. For this demo, we're going to want all our resources to be in the same resource group. So let's create one on the fly. Let's click on the Create New link. Now you can name your resource group something that makes sense to you. But for me, I'm going to call my resource group RG-SBDemo10. And then I'll click OK. Good. Now let's scroll down a bit and give our storage account a name. I'm going to call mine SBDemo10. Good. Now if we scroll down a bit more, let's set the redundancy to locally redundant storage. That's the cheapest option, and it's all we really need for this demo. Great. Now we can leave all the other options as their default. So let's skip straight through to the creation step. Click on the Review and Create button at the bottom of the screen. Good. Now, assuming Azure is happy with your configuration, go ahead and click on the Create button at the bottom of the screen once it's active. Alright, now the creation process might take a moment or two, so let's just let it do its thing while we move on to the next step. What we want to do next is create a virtual machine. So let's click on the Virtual Machines option in the Azure menu. Now at the top of the virtual machine lists, let's click on the Add button and choose the Virtual Machine option. Good. Now once again, we're presented with the option to choose a subscription and a resource group. This time, let's choose the resource group that we created while creating the storage account. Good. Now, let's name our virtual machine. I'm going to call mine, once again, SBDemo10. Perfect. Now, under the image selection, let's choose Windows Server 2019 Data Center, and it's already selected. Next, under the size selection, let's just leave the default as it is. Now notice that these sizes aren't free. Unfortunately, VMs are something that you have to pay for. But the good news is that you only pay for them while they're on. So as long as you shut it off or even delete it after our demo is done here, you won't pay much or even anything at all. Anyway, next we have the username and password. Now you can set this to whatever you want, but let's make sure it's something that you remember. So I'm going to set my username to SBDemo10 and the password to something that I won't forget. Good. Okay, next we need to set up networking. So let's click on the Networking tab at the top. Good. Now in the Virtual Network selection, let's click the Create New link. Excellent. Now let's give our VNet a name. And once again, I'm going to call mine SBDemo10. Good. Now we're going to set up the addresses. So in the address space, let's type 192.168.0.0/16. Good. Now in the subnet section, let's add a subnet called SBDemo10 and give it an address range of 192.168.1.0/24. Excellent. Now let's click OK at the bottom of the screen. Good. Now we can leave the rest of the selections as their defaults. So let's click on the Review and Create button at the bottom of the screen. And good. Now, assuming Azure is fine with all of our selections, let's click the Create button at the bottom of the screen. All right. Now the creation process may take some time. So since we need this VM for our next step, I'm going to let this be created and fast forward through this for you. All right, perfect. Our VM has been provisioned. Now in the next few demos, we're going to want to run through some code on the VM. And that means that we need to have a few prerequisites installed on that VM. So for this next part, we're going to get a little advanced. Now at the top of the Azure portal, click on the Terminal button to the right of the search box. This will open up the Azure Powershell in the cloud. Now let's just wait for it to finish loading. Now what we want to do here is add an extension to our VM. So in the terminal, I'm going to copy and paste a command. But don't worry, we'll provide that command to you so that you can copy it too. Now let's execute the command. Now notice that the command references my specific resource group and virtual machine. If yours is different, which I assume they are, you'll need to update those values. Anyway, with the command pasted in, it's now running. Now according to Microsoft, that command may take around 15 minutes to run, so I'm going to fast forward until it's done. Excellent. So now at this point, we've provisioned a storage account and a virtual machine, and we've installed our needed prerequisites. We're now ready to proceed with our next demos. Great job! In this demo, we're going to use a simple console application that runs on an Azure virtual machine and then we'll use that to upload large amounts of data to an Azure storage account in parallel activities. Okay, so the first thing we need to do is head over to the Azure web portal in our browser. Now in this demo, we're going to piggyback off our last demo and use a virtual machine to upload data to our storage account. But in order to use our storage account, we need to get a connection string from it. So let's head over to our storage account and get it. To do that, I'm going to search for my SB demo storage account in the Azure search field and select my storage account. Good. Now let's click on Access Keys in the Security and Networking section. Good. Now what we need from this screen is one of the connection strings. So let's click on the Show Keys button to expose them. And now let's copy one of the connection strings to Notepad so that we can use it later. Alright, so the next thing we have to do is connect to our VM. So let's start by navigating to our VM. Now I called my VM SBDemo10, so I'm going to search for that in my Azure search bar and then select it from the results. Excellent. Now right in the overview screen, there's a Connect button in the toolbar. So let's click on that and select RDP from the list of options. Alright, now let's click on the Download RDP file in the middle of the screen. And now let's open the RDP file and get started. Now in the RDP pop-up, let's choose to connect despite the warnings. Good. Now in the credentials box, let's enter the credentials that we set up when we created the VM and then click OK. Good. Now we can accept the connection again by clicking Yes. Good. Our VM is running. Now let's open up a command prompt. Alright. So now in our last demo, we set up some extensions from Microsoft on this VM. And those extensions include the .NET framework, some other tools, and samples that we can use to interact with storage accounts. Now the way those samples work is that they get the connection string details from environment variables. So the first thing we're going to do in this command prompt is set the needed connection variables. So let's type the following command. Set x space storage connection string, all lowercase, open quote, close quote, space /m. Okay, now inside the quotes, let's copy our connection string from Notepad. And now let's execute the command. Excellent. Next, we're going to compile one of the Microsoft samples. So let's open up another command prompt. In this command prompt, let's navigate to D, Git, Storage, .NET, Perf, Scale, App. Good. Now let's build the app that's in here. You can do that by typing .NET space build. Now this might take a moment, so I'll fast forward through that for you. Good. Now that the application is compiled, let's run it. Now the purpose of the sample application is to create 5 randomly named containers and then start uploading files to each of them. If you're interested in what the code looks like, you can inspect this folder and take a look at the upload files async method. Anyway, let's run the application and watch the outputs on the screen. We can run it by typing .NET space run. Perfect. So as you can see from the command line output, the files have been uploaded to our storage account. Or have they? Well, let's find out. Let's flip back to our browser and navigate over to our storage account. Good. Now let's click on the Storage Explorer in the left-hand menu. And next, let's expand the Blob Containers section. Nice! Look at that, we have 5 fancy new containers. Well, let's click on one of them. Huzzah! We have files! That is a fantastic job. Now let's do one more thing. Let's head back to our VM. Now let's open up yet another command prompt. Now let's execute the following command. Net stat space -a space pipe space find space /c space quote blob colon https end quote. And we'll execute that command. Good. Now what this command is doing is it's showing us the total number of connections that are opened against any blob connections. And the value can change each time we run it because the total number of connections needed to upload our files can change over time. The point of running this command is to show that we're using multiple connections to upload our files. Now, we don't have a particularly powerful VM here, so this command doesn't work so well in this case. But this is an example of ways that you can collect additional details even while data transfers are happening. Anyway, at this point, we've connected to our virtual machine, we've compiled an onboarded sample application from Microsoft, we've set up a connection to our storage account, and we've executed the application, uploaded random files to our storage account, and verified the connection counts. Great job! In this demo, we're going to update our console application that we have running on an Azure virtual machine and use it to download large amounts of data from an Azure storage account. Okay, so the first thing we need to do is head over to the Azure web portal in our browser. Now in this demo, we're going to piggyback off our last couple of demos. In the first demo, we created a storage account and a virtual machine, and we set it up so that we could execute some Microsoft sample applications. In our last demo, we connected to that VM and then we uploaded a bunch of files to our storage account. Now in this demo, we're going to connect to that same VM and use that same sample application to download data from our storage account. Alright, so the first thing we need to do is connect to our VM. So in Azure, let's search for my virtual machine by typing its name in the search bar at the very top of the screen. My VM was called SBDemo10, so I'm going to search for that and then select my VM from the results. Good. Now let's click on the Connect Toolbar button at the top of the screen and select the RDP option. Good. Now let's click on the Download RDP file button in the middle of the screen. Great. Now let's open the downloaded RDP file. Alright, so now let's connect to our VM by confirming all the dialogues and entering the credentials that we used when we created the VM. Alright, so here we are in the VM once again. Now in our last demo, we used a sample application from Microsoft to upload a bunch of files to our storage account. In that demo, we configured the connection string as an environment variable, so we don't have to do that again. Now what we're going to do in this demo is we're going to convert the existing application to download files from our storage account instead of uploading them. To do that, we need to navigate to the code. So let's open up Windows Explorer and navigate to D-Git Storage. And now let's navigate to the D drive, Git folder, and then storage.net perf scale app. Okay. Now let's open up the program.cs file in Notepad. Good. Now let's scroll down about halfway through the file until we get to the main method. Nice. Now notice that inside the try catch block, there is a line of code that performs uploads right at the top. Then, a few lines down, there's another line of code that performs downloads. And you'll notice that the download command is commented out by the 2 slashes at the beginning of the file. What we're going to do now is we're going to inverse this code. First, we're going to comment out the upload line by adding 2 slashes at the beginning of that line. And now we're going to uncomment the download line by removing the 2 slashes and the space at the beginning of that line. Excellent. Now let's save the file with a Control S and then close Notepad. Okay, so at this point we've changed the code. So that means that we need to rebuild the app. So let's open up the command prompt. Good. Now let's navigate to that same folder. Alright, now let's build the application by typing the command .net space build. Excellent. And now we can finally run the application. So still in the command prompt, let's type the command .net space run. Okay, so now it's important to understand what this code is actually doing here. On the screen, we see a bunch of output that says our app is downloading a bunch of files. And that's important because that's exactly what it's doing. It's not downloading these files one at a time, it's downloading them all at once by using a bunch of concurrent connections. In fact, let's check it out. Let's go back to the Windows Explorer. And notice now that there's a Downloads folder. Pretty cool, right? Well, let's open it up. And hey, check it out. There's a bunch of files in here. And now notice that some of them have sizes, and some of them are all set to 0 kilobytes. And that's because they haven't fully downloaded yet. But some of them are downloaded. That's awesome. Now in our last demo, we talked about being able to check on the total number of connections by executing a netstat command. So let's do that one more time. In another command prompt, we can type netstat space -a space pipe space find space /c space quote https end quote. And if we hit enter on that, we'll see the total number of HTTPS connections that have been made on this computer. So we can see that there are currently 5 connections. Each time I run the command, I may get a different number of connections. These are the concurrent number of connections that are currently out there downloading files. Anyway, at this point we've connected to our virtual machine, we've modified an existing sample application from Microsoft, we've recompiled that application, we've executed the application, downloaded all the blobs from our storage account, and discussed an option for potentially verifying the connection counts. Great job! In this demo, we're going to review and evaluate Azure storage account metrics that were generated as a result of the various upload and download activities we performed in previous demos. Okay, so the first thing we need to do is head over to the Azure web portal in our browser. Excellent. Now, in our last couple demos, we performed two major actions. First, we use a sample console application from Microsoft on a virtual machine we deployed to upload a bunch of files to a storage account. Then we modified that sample application to download all of those files from the storage account. What we're going to do in this demo is we're going to take a look at the metrics that were produced in the storage account as a result of those actions. Alright, so the first thing we want to do is navigate to our storage account. To do that, I'm going to search for my storage account in the search bar at the top of the screen. My storage account was called SBDemo10, so I'm going to type that and then click on the results. Good. Now before we get to the metrics, let's take a look at the contents of the storage account. Click on the Storage Explorer option in the left-hand menu. Great. Now let's expand the Blob Containers section. Alright, so there's all the containers that were created when we executed the Microsoft sample in upload mode. In fact, let's click on one of the containers. Nice. So now we can see that there are about 10 files in this container. 10 files times 5 containers, and we're looking at about 50 files uploaded. And so obviously that's 50 files downloaded too. And let's scroll to the right a little bit. Now notice how some of these files are about 1 gigabyte in size, and those aren't trivial blobs. So let's go take a look at the metrics and see what they tell us. Now in the left-hand menu, scroll down to the monitoring section and click on the metrics option. Good. Now notice that this produces a chart layout, and that makes sense. Metrics are calculated and produced over time, so it makes sense that we display them in a chart. Anyway, let's select a metric. In the metric pull-down selection right above the chart, select a transactions metric. Nice. Now the chart updated with some data. But what is this telling us? Well, the transactions metric tells us the number of requests that were made to our storage account. This includes both successes and failures. In our case, we're seeing a bunch of transactions, but notice that it doesn't equal the total number of files uploaded and downloaded. And that's because various operations like that can actually result in many transactions. For example, uploading a blob means connecting to the account, connecting to the container, and even possibly creating one, creating the blob, and then potentially multiple transactions just to upload the content of the blob. Next, let's change the metric to Ingress. The Ingress metric is the total amount of data that was brought into the storage account. In this case, we can see that a lot of data was transferred to the storage account. If you remember, a bunch of the blobs we have are 1 gigabyte in size, so this metric seems about right for the amount of data that it brought in. Next, let's change the metric to Egress. The Egress metric is the total amount of data that was sent out of the storage account. In this case, we can see that a smaller amount of data was transmitted out of the system. Reads are often cheaper than writes. It's also important to note that the number doesn't actually reflect billable egress. Now let's look at one more metric. Let's select Success E2e Latency. Now this metric shows us the average end-to-end latency for successful requests. From the point of the request to the point of completion, how long did an entire transaction typically take? What that means is that this value includes the time needed to process the operation within the storage account, read the request, read the data, send the response, and receive acknowledgement of that response. And this number isn't great. But then again, we're dealing with some bigger files and a slower VM that could only handle the responses so quickly. Finally, let's check one more way of looking at metrics. Now above the chart, notice that there's a button called Drill into Logs. So let's click on that button. Now in the dropdown, let's select Storage Insights. Excellent. Now in this screen, we're seeing some of the same metrics that we just saw, but we're seeing them all at once. If we scroll down, you'll see a few charts that can add some more insight into what the storage account is actually doing. For example, there's a Transactions by API name chart, and notice in the legend that there were transactions made to the GET, PUT, LIST, and other Blob API endpoints. This can help you to see what sort of operations your storage account is mostly busy with. And so there you have it. When you perform operations against a storage account, Azure will automatically collect some metrics for you that will help you gain insights into the activities your storage account is performing. In the event of issues, This can be invaluable for troubleshooting. Great job! So in this course, we've examined available Azure storage strategies. We did this by exploring determining the best Azure storage option, Azure data structure types and strategies for securing storage account data, uploading and downloading blobs with Azure storage accounts, data storage options with Azure Storage Services, creating a VM and Azure storage account, and uploading and downloading large volumes of data and monitoring with an Azure storage account. In our next course, we'll move on to examine the Azure Data Factory.